Hey guys, welcome to day 9 of CSES Problem Set. Today, the next problem in the problem set is creating strings, so let's just jump straight into it. Given a string, your task is to generate all different strings that can be created using its characters. The only input line has string length in. Each character is between A to Z. First print an integer k, the number of strings, then print k lines, the strings, in alphabetical order. Strings is n is 1, 2, 8. So n equals is a string length in, so input. So given a string, your task is to generate all different strings that can be created using its characters. So a combinatorics type question. So how would you go about this? We're given first print the number of strings, then so we're gonna have an array, like to print is gonna be an array, and then at the end we're printing len to print, and we're also for s in range for s into print s, something like this. Now the hard part is, how do we order everything? You're doing alphabetical order to start, flop the last two, flop these, How do I even start this problem? Like, we basically just generate all the permutations of the string. Doesn't Python have a permutation? Python permutation, like function? Itertools. Is itertools in standard library? Yes. Itertools.permutation. Like, we can just import itertools from itertool. Let's import permutations, and then to print equals permutations in. Like, this is obviously not what they want us to do, right? and do list uh hold on. There we go. We do this and then dot join s. Wait, no, can I do star s will have spaces, right? Just dot join. Wait. Why am I not printing anything anymore? So what I need, okay. Okay. So I need to do list to print this 120. That ain't right. I do. What do I have to print? I can't lend this. $120. That's not right. All different strings. So which strings are repeated in my case? At the A's. Let's look at only the A's for now. A, B, C, A, A, C, B. A A B A C. This one A A C A. Okay. 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 A C A B A C A B A C B A. So what are we missing? A B C. But that's the first one. Hello? Take out these guys. This is 1, 2, 3, 4, 5, 6, 8, 9, 10, 11, 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. A B C. This one. There's a duplicate in here. Okay. So we don't want permutations, we want unique permutations. So what we can do is just throw this into a set instead of a list. But is there more iter tools? There's more iter tools. Library. No, it's not. So what I can do is just make this a set, like this. And this should do it, but like obviously this question is asking for us to do it right. Oh, in alphabetical order. So we can sort it. Let me just do this. To print dot sort. I can't sort a set. So what I can do is list and then dot sort. Okay. Am I allowed to do this though? Okay, well it passed, but why does I feel like using iter tools is kind of cheating here? This is a C++ function next permutation to generate. Okay, they just use a function in C++ to do it. So I guess it's not cheating. I'm gonna look it up. CSES creating strings. There's a YouTube video over this.
What up, YouTube? Mike the Coder.
Jeez, this guy's loud. Let's see what this guy ends up doing. Okay, he's using C++. Now there's a Geeks for Geeks solution. Let's see. Yeah, basically generate all the permutations, insert it into a set, and print all the unique strings. That's basically what we did. For permutation in permutations. Okay, they use iter tools too. So if they're using iter tools, then I'm gonna say iter tools is allowed. Now, why does theirs look so complicated compared to mine? I guess it's not. They just like defined a function. But okay. I don't know. That question felt so easy compared to the the earlier ones, like Tower of Hanoi in gray code. This felt so much harder than creating strings. But okay. Well, that just means we're moving on to the next problem. There are n apples with known weights. Divide the apples into two groups so that the difference between the weights of the groups is minimal. N equals int input. Next line has n integers. Weight of each apple. So p equals list map int input dot split. Okay. In apples with known weights, your task is to divide the apples into two groups so that the difference between the weights of the groups is minimal. First input line has an integer n number of apples. Next has a list print the minimum difference between the weights. 3, 2. Group 1 has weights 2, 3, 4. Group 2 has 1. Wait, what? Divide the apples into two groups so that the differences. Oh, okay, yeah. Okay, so how do we do this? We like greedily assign weights, right? Or what? Or let me think. How do we know how to assign weights? Group 1. What's like huh. I feel like you need to sort it. If you sort it 1, 2, 3, 4, 7. You give this to one group, then you need to try to match it. Then you give this to next graded to one group, and you try to match it until there's nothing else, and then you just subtract. Now, how does this work with if you can't match it? So like 2, 3, 4. Let's get rid of 2. Let's do 3, 4, 1, 3, 4, 9. So give this one to group 1, group 2, group 2, group 2, 5, 6, 7, 8. Okay, so I think this is the solution. You sort it. P dot sort, and then group 1, group 2, for P, for apple in P. Uh, we shouldn't use the sum operation in this for loop because that'd be n squared. So we should just keep track of. Wait, what is our output supposed to be? The minimum. So we don't even need this. We can just keep track of two sums. G2, but they're integers this time. For apple and P, we do if, right, max. G2. Wait, that just tells us which is greater. But we need to check if G1 is greater than G2 is greater than G2 and G2 plus equals apple. Else, I mean G1 is less than, wait. So, okay, when do we add to G1? We add to G1, wait, what happens? If G1 equals G2, G1 plus apple. If G1 greater than G2, if G2 plus apple, wait. Okay, so now we're swapping around. If G1 is greater than G2, G2 plus equals apple. So it looks like else G1 plus equals apple. Why do I feel like it doesn't work out this well? Okay, I need a case where it goes over. So like 1, 2, 3, 4, 7. Group 1. Let's make this 5. Group 2. Group 2. Group 1. Group 2. This is 7, 8, 9, 9, 0. What do we got here? If we did it match. This works for this case, but I can't confirm if it works for all cases. But it's okay, let's just code this out and see. So if G1 greater than G2, G2 plus apple, else G1 plus apple. Print abs G1 5. So we have 1, 2, 3, 4, 7. Group 1, group 2, group 2, group 2, group 1, group 2. So this is 9, 7, 8. How are we getting 5? 6, 11. Zero, 1. Oh, we need to sort reverse. There we go. Okay. We should plop in some of my other cases to double check. 2, 3, 5, 7. Oh. Zero. Okay. What's a crazy case like 3, 1, 2, 100? Yeah. Okay, I think this is it. Okay, that was not it. Test 1 wrong. Let's not do that. Let's just do this. Correct output is 2. So, what's causing this? So, I guess it's because... but then again... 7, if we put 7 in 1, and then we try to match 7, two, this is 6. Huh, I don't actually know. This is 8. If there's 7 and 1, that's 8. And 8, but we'd have to do 7 and 2 for best case. It's 9 and 9. But then you have these cases where they like match perfectly. Right? I'm assuming that's how it is. I have a feeling this is like one of those you just try a ton of combinations. Okay, my solution is like very naive, right? Okay, how did they get 2? I get 62. The minimum difference. Bro, what? Okay, I feel like this is a. You just have to try every combination type of question now. Because you need to like backtrack to see if you find a better solution. So, like, this isn't a greedy problem. You can't just greedily do it. Right? Because sometimes, as shown in test case 2, instead of like picking a number and trying to fill it in immediately, it's better to pick 2 numbers and then fill it in. So in that case, I don't even think we need to sort it anymore. Because I mean, eventually each apple lands in some pile, and it doesn't really matter what order we do it in, as long as we check every pile. I think we just okay. What's in max in is 20, so there's not actually that many. Well, the array is 10 to the 9. Size 10 to the 9. Yeah, okay, there's only 20 apples maximum. So it's not actually that long. Or there's we can actually just simulate every permutation, right? Or every division. How many divisions are there in a there's 20 apples. Hmm. If we simulate every division, each side means 10 apples. Basically asking how many different ways can we divide 20 atoms into groups of 2? Which is just a really big fucking number, no? Or wait. It's 20 choose 10, which is 20 factorial or 10 factorial 20 minus 10 factorial, which is 10 factorial 10 factorial 20 factorial. That's still a pretty big number. That's like 100K. There's no way we just simulate everything, right? Huh. I have 20 apples. This guy, group 1 or 2? This guy, group 1 or 2? And apples. Each apple has 2 choices, for the most part. Say n equals 2. N equals 1 isn't it? Say n equals 2, then split. How many different ways? There's 2 ways. And technically, it's 1 way. N equals 4. Is A, B, C, D, A, C, B, D, A, D, B, C. Alright, this group, this group. But then there's times 2. What's 4 choose 2? 4 factorial, 2 factorial, 2 factorial. 6 different ways. Two choose 2 is 1 way. 1, 6. 3 choose 2. 3 ways. So it's 1, 3, 6. 5 factorial. Oh wait. Bro, I don't know. Basically, it's gonna be trying a lot. Like, this seems like an extreme version of a Code Forces problem. Like the civilizations one, we did this in contest. Let me see if I can find it. Social experiment. Seems like an extreme version of this. But the only difference is this has a constraint of 1. It's like either 1 or 2. It's either 0, 1, or 2. But for apples, it's like this constraint is gone. Yeah, on this question we could literally just check certain cases. It's basically 2 to the n, right? If we try everything. And 2 to the 20 is... What is 2 to the 20? 4, 8, 5, 7, 6, 10, 4, 8, 5, 7, 6. So it's 1 million different combinations. What can we keep? We probably don't need sorting anymore. Alright, I think we should do this. I don't really know where to start on this. if we try every apple, okay, so this is our sum. Our sum is 0. This is our group 1. 0. Two choices. Plus 3. Plus 0. Next, again, plus 2. Plus 0. Basically, all the subtrees are the same. So this is just a leaf node. Or not a leaf node, some temporary variable. I don't know. This variable doesn't matter. And then we have 3, 0, 2, 0, 2, 0, and 7, 0, 7, 0. And then we literally just check every path and see. Wait. This gives us the sum. We want the lowest. No. Because the lowest would just be 0, 0, 0, 0, 0. So we want the closest to? Well, if we accept 3, then the other one has to be. If we accept 2, then the other one doesn't accept 2. Well, I guess actually what we can do is sum p and then we can track like each one of these and subtract it from total sum to find the other. So it'd be minus G1 equals G2. And then we do abs G1 minus G2. That's basically this. So basically it's going to be something like this, and then we need to implement some logic here. Now what kind of logic will it be? We need to build a tree. Um, so what do we need? We need, okay, what do I even call this? Is this a DFS? Depth first search. Traversing a search or searching a tree, exploring as far as possible along a single branch before backtracking. Okay. Now how do I build a DFS? Uh, well, technically, so what do we actually want from G1? kind of struggling to visualize this. Can I get three numbers? Like 1, 2, 3. But it's not all the way down to 3, right? Well, they never specified even groups, so yes, technically this is possible. Right, where a group has nothing in it, and one group has everything in it. So this would be 3, 4, 5, 6. 1, 4, 1, 5, 2, 3, 0. Okay. Our total is 6. G2 equals 6 minus these. Our answer is G2 minus G1. Six is total. So G2 is total minus 2G2, or 2G1. So we don't even, well, yeah, technically I can just do this. Doesn't really mean too much. I save a variable. But now, so we're looking for 3. We can stop when it's exactly half. So DFS, and we want we want to know what level we're on. Four. 1, 2, 3. In this case, n equals 3. So when do we break out of this? We break So, okay. Oh, that's a bad word. Sum. And then if I is equal to n, so basically if we get to the n, so we can't call this sum. It's technically a prefix sum. It's sum of all the chosen elements before it. What do we do when I gets to n? We do this. Okay, so we need to track a toPrint variable. Print. Can do this, and then we do min. We do toPrint equals min toPrint this, and then here we do toPrint. And we're done. And then we need to call DFS in here. If we accept the apple, we go to the next level. Well, either way we have to go to the next level. But we choose it's like this plus P PI is PI P is 1, 2, 3 on level 0, 1, 2, and if it's equal to 3, yeah, PI. Right? Uh, so, and then, so we start on level 0 with a sum of 0. So instead of thinking of these as plus 1, each of these is a prefix sum, actually. So I'm kind of envisioning this tree wrong. Although, either way, okay, so this is what the tree actually looks like. It doesn't actually matter, but it's basically 0, and each node is the sum. So 1, okay, let's do 0. How do I make this look neat? 1, 0. 1 plus 2 is 3, plus 0 is 1, plus 2 plus 0, then 3 plus 3 is 6, plus 0 is 3, 1 plus 3 is 4, plus 0 is 1. Okay, definitely not enough room. Hold on, let's make use of the tools given to us. Alright, and then let's connect all this shit. We got our tree. This is 0, 1, 3, 6, 3, 3 plus, this is 1, 4, 1, and this is 0, 0, 0, 0 plus 2, 2, this is plus 3 is 5, 0 plus 3 is 3. So it looks something like this, basically. Now we check. This is level 0, I equals 1, I equals 2, I equals... No. Yes? Wait, no. No. We start at 0, we increment 1. We start at 0, starting here. Increment. We eventually pass in 3. Right, and when we get there, we set yes, this should be right. If 2 print equals in, yeah, because we find all the sums. This hurts my head. So we call DFS0. We create this node. Then we call DFS 1 1 here. And we create 1 0 here. And then we go through I is 1, which is not equal to n, so we don't do this. So then we create DFS2, three, and 2 1, and then we do the other side from this one, 1, or this is DFS2, 2, and 2, 0. Bro, this shit is so confusing. Can I do some print statements? It's our level in our prefix sum. Case input cannot access local variable. I guess G1 doesn't. Wait. Cannot access. Wait times G1. Let me think. It's not G1, it's prefix sum. We don't need G1 anymore. What can it not access? To print. Okay, so 0 0 1 1 2, 3, 3, 6, and 3, 3, 2, 1. Okay, yeah. Okay, so this is DFS. So what it's doing is bum 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 bum, and we reach an end. We go back, and then we find another end. We go back. We go back. Then boom boom, reach the end. Go back. Reach another end. Go back. Go back. Go back. Go back. And then boom 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 boom. Reach an end. Go back. Boom. Reach another end. Go back. Go back. And boom 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 boom. Reach an end. Go back. Boom. Reach another end. And then end here. And then now yeah, our expected output is indeed 0. Because we were technically looking for a direct half of the total sum. Yeah. So, okay, what was confusing me earlier was I think I was trying to BFS, like where you create this, and then you create this. This one's TFS, so you create all the way to the end, and then backtrack, and then to the end, and then backtrack, and then to the end, and then backtrack, and then to the end, and backtrack, and then to the end, backtrack to the end, backtrack to the end, backtrack to the end. Yeah. Okay, this makes a lot more sense to me. And yeah, my code is doing that. Because if let me think. Where was the question we did the other day? Tower of Hanoi. This one was. Let me think. This one was technically DFS too, right? It's like you call, and then until you get to the very end, output, then output, then call, output, and you backtrack. This is DFS as well. Have we done a BFS question? I don't know. But okay. I'll just double check if everything works here. Get rid of Hanoi. Where's my extra print statement? Here. Okay, it's working. There we go. Analysis. Total sum of divisions is 2 to the n. Since n is at most 20, we can efficiently go through all divisions and select the optimal division where the difference of the sums is minimal. But doing this is very slow. Like in general, right? Each division of apples corresponds to a bit string of length n where each bit determines the group of an apple belongs to. For example, if the weights are this, the bit string 00101 means the first group has weights 3, 2, 4, and the second group. Oh. So they're using like bit masking, which I've only touched kind of once. And I didn't even touch like straight up bit masking, it was like the binary representation of n. If y'all remember the question huge pile, we did it in a contest. It was a contest question that I uploaded a little while ago, which I needed help on. But okay, so what did they do? Go through all divisions and select the optimal division where the difference is minimal. Okay, so it looks like we defined P diff equals 1E9 for B shift Okay, I don't really get it. I like my solution a little bit more. Alright. How long has it been? Hour 20, 29? Let's just call it here. If y'all enjoyed this video, be sure to like and subscribe. And I'll see y'all guys tomorrow. Bye.